For this section, we're going to be learning about applying L'Hopital's rule, and I know it's a funny way to word to pronounce that way. That's the pronunciation, L'Hopital. And there are different spellings. You might see different textbooks. So L'Hopital's rule is used when we have the situation, the indeterminate form, usually a 0 over 0, but also an infinity over infinity. It could also be if you have the case of like 0 to the 0, or 0 to the infinity, or infinity to the 0. So we'll look at all these different cases. So as I said, the indeterminate form there. And the first type we'll look at is if the limit would be 0 over 0. The way L'Hopital's rule works is you can take the derivative of the numerator and the derivative of the denominator. And this is not the quotient rule. It's just taking the derivative of the numerator of the derivative of the denominator, and you'd end up with the same limit. That's what this part here is saying. So if f and g are differentiable functions over an open interval, then the limit, and if the limit of as x approaches a of f of x equals 0 and g of x, as x approaches a g of x equals 0. So these limits would be 0 over 0 in indeterminate form. Then you could take their derivatives and see what happens. And the limit of the derivatives of each, the quotient of their derivatives is the same as the limit of the original. Okay, so here's our first set of examples. We're going to evaluate each of the following by applying L'Hopital's rule. So the first one, it says limit as x approaches 0 of 1 minus cosine x over x. And so you put a 0 in there in the numerator, you're going to get 1 minus 1, which is 0 over 0. So if we apply L'Hopital's rule, and I like to do a little h here, I learned that from another textbook, just to show what's happened from step to step. And this next step, I'm applying L'Hopital's rule. Limit as x approaches 0. The derivative of 1 is 0. The derivative of cosine is negative sine, so we'll end up with a positive sine of x, because it's a minus cosine, over 1. Now if we plug in the 0, we end up with a sine of 0 over 1, which is 0 over 1, which is 0. Next one, we have limit as x approaches 1 of sine of pi x over natural log of x. So as you put that 1 in there for x, you end up with sine of pi, which is 0, over natural log of 1 is 0. So if again we apply L'Hopital's rule, we have the limit as x approaches 1 of pi times cosine of pi x over 1 over x. And so what's that going to be? That's going to be the limit as x approaches 1 of, or I don't need to worry about the 0. I was thinking that was a 0 down below. Sorry about that. So it's going to be 1 goes in there, so it's going to be pi times cosine of pi times 1 over 1 over 1. So that's pi times, and cosine of pi is negative 1, so it's negative 1. So the answer is negative pi. So that's our limit. Let's look at the next one. Limit as x approaches infinity of e to the 1 over x. Well, that's e to the 0 basically. So e to the 0 is 1. 1 minus 1 is 0 on top. 1 over infinity is considered 0. So again, if we apply L'Hopital's rule, we'll have the limit as x approaches infinity of the derivative of e to the 1 over x is e to the 1 over x times the derivative of 1 over x, which is negative 1 over x squared, divided by negative 1 over x squared. And so this coefficient then would divide out, and you'd end up with just e to the 1 over x, so that's e to the 1 over infinity, which is e to the 0, which is 1. And for the last one, if we apply L'Hopital's rule, which it's appropriate because you end up with, again, a 0 over 0. So L'Hopital's rule applied, you get the limit as x goes to infinity of cosine of x minus 1 over 2x. So if I applied it again, that's not an infinity, sorry, that's 0. If I applied that again, I'll end up with a 1 minus 1 over 0, kind of like a. So I'm going to apply L'Hopital's rule a second time. So we have the limit as x goes to 0 of negative sine x over 2. And so that's going to give us 0 over 2, which is 0. Okay, that's how we do L'Hopital's rule. Let's go to another example. Okay, evaluate the limit as x approaches 0 of x over tangent of x. So right now it's 0 over 0 is the limit. So L'Hopital's rule applies. So we will apply L'Hopital's rule. And we would have the limit as x approaches 0 of 1 over secant squared x. And so now it's not going to be 0 over 0 case. We'd have a 1 over secant of 0. And that amount gets squared. So it's 1 over 1, so it's 1. Now there's another indeterminate case, the infinity over infinity case, but the same rule applies. So here we have, and we've seen something like this earlier. You also saw it in your pre-calculus days with the limit as x approaches infinity of 3x plus 5 over 2x plus 1. If here you apply L'Hopital's rule, you get the limit as x approaches infinity of 3 over 2, which is 3/2. And the next one, this is approaching 0 from the positive side because of the natural log part. We had to specify that. We have the limit, also the cotangent. Limit as x approaches 0 from the right side of 1 over x over let's see, 1 over x over negative cosecant squared x. Okay, now we can write this a little differently. We could write this as the limit as x goes to 0 of putting x on the bottom, and then cosecant is 1 over sine, so that'd be negative sine squared x up on top. And with that, we can take L'Hopital's rule again, apply it, and we have the limit as x approaches 0 from the positive side. I forgot my right side there. And we'd have negative sine x cosine of x. Oh, I forgot my 2. Negative 2 times sine x cosine x. And the derivative of x is just 1. So plugging in the 0, you end up with a 0 on top and a 1 on bottom, so it's 0. This is one of those cases, by the way, the infinity over infinity, which infinity is bigger? And so in this case, the bottom infinity is bigger than the top infinity, so it drowns it out. Okay, let's see what else we have. Evaluate the limit as x approaches 0 of 5x. So, same thing, infinity over infinity. That's what we're going to have. So we'll apply L'Hopital's rule. Why my h's get funkier and funkier. Limit as x goes to infinity of 1 over x over 5. So you can think of this as limit as x approaches infinity of 1 over 5x. So that's going to be 1 over infinity, which is 0. Another one here. Consider the limit as x squared plus 5, x squared plus 5 over 3x plus 4 as x approaches 1. So in this case, does L'Hopital's rule apply? Well, you end up, if you plugged in that 1, you'd have the limit as x goes to 1 of x squared plus 5 over 3x plus 4. You'd end up with 1 plus 5 over 3 plus 4, 6 over 7. So L'Hopital's rule does not apply. Okay, well, here's another example for us. Explain why we cannot apply L'Hopital's rule here. So if we look at the limit as x goes to 0 of cosine of x, 0 from the right side, over x, we would have cosine of 0 over 0, which is going to be 1 over 0, which is considered infinity. So again, it's not 0 over 0. It's not the indeterminate case. So L'Hopital's rule does not apply. Okay, got one more here. It didn't print out, so I'll just write it in. It says, use L'Hopital's rule to evaluate the limit as x approaches infinity of 7x squared minus 2x over 4x squared plus 3. And so if we apply L'Hopital's rule once, we'll have the limit as x approaches infinity of 14x minus 2 over 8x. And then we could apply it again, because we still would have the infinity over infinity case. We'd have 14 over 8. So 14 over 8 is 14/8. And another way to do this is to have said, if you recall this, that was part A, this is part B. If you did it without L'Hopital's rule, you do the limit as x goes to infinity of 7x squared minus 2x over 4x squared plus 3. We can multiply 1 over x squared over 1 over x squared. That's the x with the highest power. That gives us the limit as x approaches infinity of 7 minus 2 over x over 4 plus 3 over x squared. Now we apply that infinity. We'd have 7 minus 2 over infinity over 4 plus 3 over infinity. So that's going to be 7 over 4. By the way, this reduces to 7 over 4. So, see, in general, our limit as x approaches infinity of 7x squared minus 2x over 4x squared plus 3 equals 7/4. Either which way you do it. Okay, hope you enjoyed that. We got a couple more things to look at with L'Hopital's rule to finish off this section.